So in this last week, I need to finish off by introducing this Nika immutability. So first of all, let's give the definition. So if I have a quasi-lattice order semigroup, last week we defined their universal semigroup C-star algebra. And also we have the reduced C-star algebra, basically the left regular representation. So if they're isomorphic as to C-star algebras, then we say it's Nika immutable. So this is really trying to mimic what we have in the case of a group. All right, so we saw that the group is immutable if and only if its full and reduced C-star algebra are the same. Okay, so we're trying to do the same for semigroup. And first of all, let's just want to derive a very useful technique of proving this Nika immutability. It's called the faithful conditional expectation. So I'll say what I mean. But first of all, let's prove the following slightly technical lemma. So suppose I have a Nika covariant representation of my semigroup. Okay, so you can think about this Nika covariant representation kind of generate a concrete C-star algebra. You just take all the W of X, and you take their adjoints and you multiply them together and take the linear span, and you get an algebra, and you close it up in B of H. That's your C-star algebra. But it's actually very easy to describe the C-star algebra when you have Nika covariance. Essentially, it's just the closure of these Wx, Wy star. Okay, so you can the span of these Wx, Wy star. You only have one and times its adjoint. That's enough to kind of span a dense subset. This is not only a dense inside there; it's actually just a dense algebra inside there, right? So the idea is just really simple. So if you have say anything like a Wx star and then you have a W of Y, then what you can do is you can always move the adjoint to the other side. Okay, so what I mean by that is that first of all, let's use the fact that the W is isometric. So I have a Wx star Wx. And then I have my Wx star Wy. Okay, this is by isometry, that's identity. And I put a Wy star Wy. This is also identity. Okay, so I can make them inside. And these two are just the range projection of the Wx and Wy. So by the Nika covariance, they will become the W of their least common upper bound. Okay, so W of xvy, I have a star here, and then I have a wy. Of course, if x and y have no common upper bound, then this is just 0. Okay, so this is it just disappeared. Okay, but in any case, in this case, I can now have this xy, xvy is greater than or equal to x. So this is equals to x times some p. Okay, or another way of writing this as x inverse of xvy. Okay, so it's equals to x times something inside your semigroup. So now you have a Wx star on the left, so you can pull out this Wx and get it cancelled. So what you have is that you have W of x inverse of xvy, and you do the same on the other side, and just you move the Wy to the other side. So you essentially get the same thing. Okay, you have a y inverse of xvy. Okay, the star. So what this proves is that whenever you have these adjoint on the left, you can move it to the right. So basically, if you take the span of all the Wx, Wy star, then it becomes an algebra. Okay, so if you let A to be the span of all the Wx, Wy star, and you can imagine if you have a Wx, Wy star times a W of x prime, Wy prime star, then the star can always move to the other side, or maybe it becomes 0, but in any case, it's still in this form, okay, it's still inside A. Okay, so this is either equals to 0 or is equal to, say, W of x, sum of W times some Y star, okay? But the point is, no matter what you have, it's still inside A. So this A is really an algebra. And because it's an algebra like that, so any kind of words of any multiple of your W with its adjoint can be written as an element inside A. So clearly, this A is dense. Okay, so that's going to be dense. All right, so we now have a pretty good description of what this semigroup C-star algebra is. Here, W can be any covariant one, so it's still true if you just take the universal one or the reduced one. So now we introduce a very useful technique called the faithful conditional expectation. So this is kind of a standard technique in proving amenability these days. So what we have is that suppose I have an isometric covariant representation, let's call it W, and recall every such representation kind of induce a representation of the diagonal algebra, basically sending the 1p to the range projection. I should say WP, WP star. All right, suppose this representation is faithful on the diagonal algebra, so we have a characterization when it's faithful, basically multiply a bunch of projections, and if it's non-zero, then it's faithful. Then what I have is that actually there exists a contracted map that maps from their C-star algebra generated by these isometries to the diagonal algebra. Basically, what it does is that it kills off all the off-diagonal. Okay, so the Wx, Wy star will be mapped to 0 if x and y are different. So here the delta xy is the counterpart delta. So it gives you 0 if x and y are different, and if is equal to 1 if x is equal to y. Okay. So to prove this is a rather technical one, so I'll just give a quick sketch, and now I'll omit a bunch of detail. But essentially the idea is that, well, first of all, the Wx, Wy star, we just saw they span a dense subalgebra inside your C-star algebra. All right, so we just need to consider the following. So we just need, first of all, to show that for every say lambda of x and y inside some finite set f, I do a finite linear combination of these wx, wy star. So here f is finite. Then if I want to show this phi is contractive, I just need to show it's contractive on all of these elements. So we need to prove the following. So if I apply phi to this, essentially what I have is the summation of the lambda xx of the wx star. I want to show if phi is contractive, so this is going to be less than equals to the summation of when you have everything wx, wy star. Okay, so that's what we need. And to show that, it suffices to do the following. Suffices to show that there exists some orthogonal projections, let's call them Q, so that first of all, it satisfies some conditions. So first of all, the Q will kill off all your off-diagonal entries. Okay, so if you have an x and y, they're different, then you multiply Q on either side. This is equal to 0, okay, for every x not equal to y. So here x and y are in your finite set. And secondly, this Q will kind of Q will chop your diagonal part to the norm. Okay, so what I mean by that is that if you multiply Q to the summation of all the diagonal part, basically that part is whatever Q cannot Q off. Okay, so that's what you have, and that will give you the same norm as what you have here. Okay, that the wx star. Okay. So if you can prove if you can find such Q, okay, then what you want to prove is kind of trivial now. So if you want to have this summation of all the lambda x, wx star, now this becomes the Q of the same thing. But Q will also Q off the off-diagonal entry. So this is essentially Q times the off-diagonal. You add all the off-diagonal back. You have lambda xy, wx, wy star, and then you put the Q back. But Q is an orthogonal projection, so it has norm less than equal to 1. So it's certainly less than equals to the summation of when you put everything here without the Q. Okay, lambda xy, wx, wy star. Okay, so from there, if you can find such a Q, okay, then this claim can be proved. All right, so now it's just a matter of finding such a Q. Okay, so it will take it's a rather technical proof. I'll just give you a brief idea. So first of all, let's see we prove that when we estimate the norm of a element like these lambda x, wx, w star when we talk about the representation of the diagonal algebra. We show that this is actually by dividing this this range projection into orthogonal kind of sub-projections. This is equals to the summation of x equals to a of some lambda xx, okay, for some a containing f, okay, and the corresponding qa, let's say w, is essentially just equals to the product of, so for everything x inside A, you multiply the range projection, and then for x not inside A but in F, okay, you multiply the orthogonal of its range projection, okay. So that's kind of how you divide this range projection wx, wx star into disjoint ones. And for some of them, it will achieve the maximum. Okay, so for some QAW, where this projection is non-zero, it can attain the maximum, and that will give you the norm. All right. And so what we have is that, well, so if you look at what happens when you multiply this QA, let's say W here, so if you have a lambda XX, WX, WX star, and then if you just multiply the QAW, so essentially, remember, this one will decompose as a bunch of summations of, say, y inside B, lambda y, and then you have the QBW, okay, you decompose as a linear combination of these basic orthogonal projections. And all of these Qs are disjoint to each other, okay, they're partition of the identity if you wish. So that if you multiply the QAW on the right-hand side, it will pick up only the QAW component. Okay, so this will become the summation of x inside A of the lambda xx QAW. Okay, so of course, if you move the multiply another QAW on the other side, then you get another copy of QAW. So the norm of this will certainly be equal to the summation of the lambda xx, okay? Well, but this projection is slightly too big, okay? So one other thing you want to observe is that for every x and y inside F, okay? So if x is not inside A or y is not inside A, then your wx times wy star, let's say x is not inside A, okay, so you will have a QAW here and then a QAW here. This one will give you 0, okay. The reason is just really, say if your x is not inside A, then the range projection of this x will be orthogonal to this QAW, but you have a wx here, okay, so you'll map a vector into the range of the w of x, which is orthogonal to QAW, so it returns 0, okay, the same thing on the other side. You can also derive it algebraically, okay, inside your QAW, if your x is not inside A, you have an identity minus wx, wx star, and you multiply the wx on the right, you get a wx minus wx, which is 0, okay, so in any case, they'll kill off all these off-diagonal entries if your x and y are not inside A. Okay, but it doesn't kill off those when x and y are inside A. Okay, that's a problem. So what we need to do is that we need to kind of cut down this QAW by a little bit. Okay, so that's where all the technical condition came from. So for every x and y inside your A, what you want to do is that, let's say your x and y, they're less than equals to the least upper bound of A, let's call it A here. All right, and what you can define is you define the d of xy to be the following. So let me just copy the formula here. You do the x inverse A, x and y, they're less than equal to A, so x inverse A is an element inside the semigroup. Okay, so I'm not taking the inverse of any group element, okay? And I have x inverse A and the y inverse A. They may have a common upper bound, they may not. In that case, it's just the infinity, everything will be 0. But now I take their upper bound and I multiply I cancel out the x inverse A on the left, okay? Again, this is, I'm just canceling things inside the semigroup. I'm not taking things in the group. So this is a semigroup element. So that's if I have the x inverse A inverse times whatever this thing inside is not equal to identity. And if it's equals to the identity, then I use the y. Okay, so I use y inverse a inverse the same formula inside x inverse a, y inverse a. It's just some really technical condition. Okay, so the idea is that first of all, this dxy are never equal to 0, never equals to the identity. Okay. And second of all, if you do the following, so if you let Q to be, so you have your QA pi, which is already a projection. I just want to cut it down a little bit further. So I want to say for every x and y not equals to y and x, y are inside A, that's the part I need to cut down further. So what I do is I do WA star, that's the range projection of all these, the least common upper bound of things in A. And then I have a WA d times dxy, and then I have a WA dxy, the whole thing star, okay? So I multiply all these. The idea is these will kill off these the last bit when x and y are inside A and if they're different, okay? So I will just write it as a fact, okay? So it's really technical to check everything, but you can check that for every x and y inside A, then this Q will kill off this off-diagonal entries, okay? So if x and y are different, okay, then Q, if you multiply Q on either side, then you get a 0, okay? And also this Q is certainly non-zero, okay, because of some technical conditions again, okay? And because your Q is a sub-projection of your QA pi, so this Q times WX, WY star Q will also be equal to 0 if one of the XY, well, say one of X and Y are not inside A, but of course they have to be inside F, okay? So basically this Q will satisfy what we have, okay? So as a result, Q is the desired projection, and therefore we finish the proof, okay? So in other words, whenever we have a faithful representation on the diagonal algebra, we can also always have a contracted representation, and this is called sometimes called a conditional expectation. So as a corollary, what we have is that if you take the universal one, okay, so let's say take the universal representation. So for the universal representation, we sometimes write it as the I pi and IP as a covariant, universal covariant representation. Then there exists a big map phi from the C star, the universal C star algebra to the diagonal algebra, which is we know is isomorphic to the d lambda. Basically, what it does is kill off this diagonal entry. Okay, so lambda xy. So I have IPX, IP of y star. It will be mapped into the summation of these lambda xx. Okay, I only take the diagonal ones. Okay. IP of x star, all right? So here x and y are inside some finite set. We saw they're dense, okay? So there exists such a map which is contracted, okay? All right, so this phi is called a conditional expectation. So we call this phi a conditional expectation. So it's really just taking the diagonal part, all right? All right, so the roadmap for the proving this technique of proving things are nearly commutable is now inside this picture. So I have the universal one. This is C star of P, C star U of P. The C star U of P, I know I can always have an onto homomorphism onto the reduced C star algebra because the universal one takes the direct sum of all the representations. So the question is really just when is this lambda is a conditional, well, when this lambda is faithful, is injective. And now what I have is that this picture, so I have a conditional expectation, let's call it phi, onto the diagonal algebra d of u, okay? And I can actually do the same thing. I can do a little phi, which go from the d of lambda, okay? So as it turns out, this phi is always somehow faithful on the positive element. I'm going to explain in the next video, but there's some kind of injectivity on that part, okay? And what you have is that this du is actually isomorphic to this d of lambda, okay? We saw their diagonal algebra are always the same, okay? These two are kind of isomorphic. And you see this diagram commute, so whether it go this way or whether it go the other way, doesn't really matter, you get the same thing. All right, so this just essentially just translate into some faithfulness of this big phi, okay? If your lambda is faithful, then going the upper way, going by lambda, and then the conditional expectation on your reduced one somehow is faithful, then it's just translate into the other one, okay? So I want to give the condition. So here's the big theorem we want to prove. We need to give we say this phi is faithful if for every b inside your universal C-star algebra, if you have a phi of b star or b star b is equal to 0, okay, then b has to equal to 0, okay? So this is, in other words, this is really just faithful on positive elements, okay? Of course, your phi is mapping from a big algebra to a smaller one. There's no way it's a faithful, I say, just a map. But as long as it's faithful on the positive elements, then we say it's a faithful conditional expectation. The big theorem is that this is equivalent to being Nika amenable. Okay, so your P is Nika amenable. That's if and only if this phi from your full to the diagonal part is a faithful conditional expectation, right? So that's the main theorem we're going to prove.